Welcome to a new episode of AI Research Radar, where we showcase the most cutting-edge developments in the field of artificial intelligence. Join us as we shine a spotlight on the latest advancements and breakthroughs in AI research. From machine learning to natural language processing, AI Research Radar covers it all to keep you informed on the forefront of AI innovation.
The paper titled Social Learning Towards Collaborative Learning with Large Language Models introduces two methods for knowledge transfer between large language models, LLMs, in a privacy-aware manner, inspired by the concept of social learning. Verbal social learning, sharing instructions. This method involves a detailed description of a behavior, followed by instructions on how to engage in the behavior. Teacher agents generate these instructions based on their private data. These instructions are then shared with the student, who integrates them into its prompt. Live models, sharing examples. This method involves an individual demonstrating the desired behavior, which the learner then imitates. A technique used that allows LLMs to perform well on a new task is including examples of that task in the prompt, a technique called few-shot learning. Teachers generate artificial examples based on the real data. The student then selects from the generated examples and adds the selected ones to its prompt. The paper also introduces the concept of a social learning protocol, which defines the response functions of teachers and the student in the social learning process. The teacher's response is defined as the message sent to the student in response to the message received from the student. The student's response is defined as the message sent to the teachers in response to the messages received from the teachers, and the creation of an updated prompt. The paper also discusses the use of a voting aggregator as a more sophisticated method of selecting examples. In this method, teachers vote on their preferred examples, and the aggregator selects the example with the most votes. Finally, the paper introduces the use of the secret sharer technique to measure how much social learning can memorize sensitive information included in the private examples. This technique works by inserting artificial secret data points, called canaries, into the training data set. The score assigned by the model to the canary included in the data is compared with the scores of the comparison data points that were not included in the training data. The authors conducted several experiments to validate the effectiveness of the social learning framework. The experiments were designed to evaluate two primary approaches for knowledge transfer between large language models, LLMs generating abstract prompts, instructions, and generating synthetic examples. Datasets. The experiments were conducted across diverse datasets, including SMS spam, a dataset of SMS messages classified into spam and not spam classes. Lambada, a closed task where the last word of a sentence is removed and the task is recovering the word based on the context. Boolean questions, BoolQ, a dataset of a context, question, and answer triplets. The model is asked to provide a yes or no answer to the question based on the given context. Grade School Math, GSM-8K, a set of mathematical questions annotated with the final answer as well as the trace to reach the answer. Random Insertion, an artificial dataset where a random punctuation mark is inserted after each character of a word. The answer to the task is the original word without the punctuation marks. Methods. Two primary methods were evaluated. Verbal social learning, sharing instructions. In this method, teacher agents generate instructions based on their private data. These instructions are then shared with the student, who integrates the instructions into its prompt. Live models, sharing examples. In this method, teachers generate artificial examples based on their private data. These examples are then shared with the student, who integrates them into its prompt. Evaluation metrics. The effectiveness of the methods was evaluated based on performance. The performance of the student model was compared to results with the use of original labels and prompts. The performance was measured in terms of accuracy across diverse datasets. Memorization. The authors quantified memorization as a proxy for privacy loss. They adapted the secret sharer technique to measure how much social learning can memorize sensitive information included in the private examples. Results. The results showed that the social learning methods yielded promising results with low memorization of the original data. The performance using these methods was comparable to results with the use of original labels and prompts. The secret sharer experiment showed that while some memorization occurred, the average rank was quite close to the no memorization baseline, indicating that the methods were effective in preserving privacy.
This is AI Research Radar. Now, we will be delving into the next paper on our agenda.
The researchers in the paper titled Heuristic Reasoning in AI, Instrumental Use and Mimetic Absorption proposed a series of innovative experiments to investigate heuristic reasoning within artificial intelligence (AI) systems. The experiments were designed to uncover the conditions under which AI systems transition between exhaustive logical processing and the use of cognitive shortcuts, heuristics. The experiments included variations of the classic Linda problem, a novel application of the beauty contest game, and tests of social intelligence. In the Linda problem variations, the researchers tested the AI's responses to the classic problem and its minor variants. They also introduced scenarios involving both existing and hypothetical AIs to assess the effect of familiarity on the AI's decision-making process. In the beauty contest game, the researchers manipulated computational load by varying the number of reasoning rounds and the fraction of the average vote considered the winning value. They evaluated heuristic adoption across two OpenAI models with varying capacities and training regimens, GPT-4 and GPT-4 In the tests of social intelligence, the researchers developed and applied 3 sets of novel tests of AI cognition across 3 distinct psychological domains. They used a questionnaire similar to those used to assess the Barnum effect to probe the sensitivity of AI systems to various social priming contexts. The researchers also distinguished between the mimetic absorption of heuristics and their instrumental utilization. They proposed that mimetic absorption pertains to the imitation of patterns in human interactions and human-generated data, while the employment of heuristics as an instrument points to intrinsic optimizations, whereby environmental regularities shape efficient but biased cognitive processes. Experimental work to validate the methods. The experimental work conducted to validate the methods in the study involved a series of innovative experiments designed to probe the heuristic reasoning within artificial intelligence (AI) systems. The experiments were divided into 3 main categories: conjunction fallacy, social intelligence, and bounded rationality. Conjunction fallacy. The researchers conducted 4 distinct studies to explore the emergence of heuristics within the context of the conjunction fallacy. This cognitive bias leads humans to erroneously judge the likelihood of combined events as being greater than that of a single constituent event, thereby contradicting the principles of probability theory. Linda problem variants. The first study examined the AI's responses to the classic Linda problem and its minor variants. The AI consistently selected the single logically valid option, demonstrating an effective application of probability theory. Occupation and interest inference. In the second study, the AI was presented with a unique occupation and interest, and a paragraph exemplifying that interest. The AI was then asked to infer the probability of 2 nested options. The AI showed a significant increase in the selection of the conjunctive option. Authorship attribution. The third study introduced a novel testing paradigm where the AI was presented with a paragraph and asked to determine the likelihood of authorship between 2 nested options. The AI again showed a significant increase in the selection of the conjunctive option. AI model recognition. The fourth study introduced scenarios involving both existing and hypothetical AIs to assess the effect of familiarity on the AI's decision-making process. The AI's performance notably diverged depending on the familiarity of the AI models presented in the scenarios. Social intelligence. The researchers developed and applied a novel methodology to test the AI's responses to a self-assessment questionnaire preceded by primes designed to elicit either self-referential or peer-referential contexts. The findings indicated that the AI exhibited a competitive yet modest persona when the assessment was framed as being developed for its competitors, in contrast to its default confident self-portrayal. Bounded rationality. The researchers devised an iterated reasoning task that pushes large language models beyond their implicit processing limitations. When resources permit, systems display exhaustive computational analysis. However, under sharply binding loads, the very same systems reflexively default to relying on simplified heuristics. This abrupt, non-compensatory transition in the problem-solving approach indicates an implicit encoding within AI architecture to efficiently balance accuracy and effort allocations based on environmental resources.
This is AI Research Radar. Now, we will be delving into the next paper on our agenda.
The paper titled MEGAVERSE, Benchmarking Large Language Models Across Languages, Modalities, Models, and Tasks, presents a comprehensive methodology for benchmarking large language models, LLMs, across languages, modalities, models, and tasks. The methods and experimental work used in the study are detailed below. Methods. Dataset selection. The study includes 22 datasets covering 83 languages, including low-resource and African languages, to evaluate the multilingual capabilities of LLMs. The datasets span a variety of NLP tasks, e.g., natural language inference, question answering, sentiment analysis, and modalities, text and multimodal, ensuring a comprehensive assessment. Datasets were chosen to represent diverse language families and scripts, including newly added datasets like AfriQA, Belebele, IN22, MARVL, XM3600, and XRISAWOZ for broader coverage. Model evaluation. The study benchmarks 9 state-of-the-art text LLMs, e.g., GPT-3.5 Turbo, GPT-4, Palm-2, and multimodal models, e.g., GPT for Vision, Gemini Pro Vision, across the selected datasets. Models are evaluated using task-specific metrics such as accuracy, F1 score, and RUGEL, depending on the nature of the task. Prompting strategies. The study employs various prompting strategies, including monolingual prompting, zero-shot cross-lingual prompting, translate test prompting, and task-specific prompts. These strategies are used to guide the model's responses and evaluate its performance in different scenarios. Contamination analysis. The study conducts a contamination analysis to assess whether models have been exposed to the evaluation benchmarks during training, which could inflate their performance. Different techniques are used for commercial and open-source models to detect contamination. Experimental setup. The study mentions limitations due to computational resources, affecting the number of experiments and the depth of analysis in certain areas. Efforts are made to ensure experiments are reproducible, including setting deterministic output conditions for models. Experimental work. Selection of models and datasets. The study evaluated 9 new state-of-the-art text LLMs, including GPT-3.5 Turbo, GPT-4, Palm-2, Gemini Pro, Mistral, Llama 2, and Gemma, across various sizes and capabilities. It also compared the performance of multimodal models such as LLVA models, GPT for Vision, and Gemini Pro Vision on multilingual multimodal datasets. The benchmark comprised 22 datasets covering 83 languages and tasks ranging from natural language inference, NLI, and question answering, QA, to sentiment analysis and machine translation. Experimental setup. The study explored different prompting strategies, including monolingual prompting, zero-shot cross-lingual prompting, and translate test prompting, to evaluate the model's performance across various languages and tasks. Depending on the task, appropriate evaluation metrics such as accuracy, F1 score, BLEU score, and others were used to assess model performance comprehensively. Key experiments conducted. The experiments aim to assess the model's ability to understand and generate text in languages other than English, focusing on both high-resource and low-resource languages. For models capable of processing both text and visual inputs, experiments were conducted on multimodal datasets. A thorough investigation into data contamination was performed to understand how the inclusion of evaluation benchmarks in training data affects the model's performance on multilingual tasks. The study evaluated the models on a diverse set of tasks to understand their generalization capabilities and limitations across different types of NLP challenges. Results and analysis. The experiment revealed that larger models like GPT-4, Gemini Pro, and Palm-2 generally outperformed smaller models across various tasks, particularly in low-resource languages. GPT-4 consistently showed superior performance over other models in many datasets, highlighting its effectiveness in multilingual understanding and generation. The contamination study indicated that several models are likely contaminated with multilingual evaluation benchmarks, affecting their performance and necessitating methods to detect and handle such contamination. The experimental work provided a comprehensive evaluation of the current state of LLMs across a wide range of languages, modalities, and tasks. It highlighted the strengths and limitations of existing models, offering insights into areas requiring further research and development to build more effective and inclusive multilingual and multimodal LLMs.
Thank you for joining us for this episode of AI Research Radar. Be sure to stay tuned for our next episode where we will showcase the latest innovations in AI research. If you enjoyed the content, please consider subscribing and liking the video.